Hello, welcome to session number 4 in the series Clocking Circuits. My name is Anurag Nigam, and this time I'm going to cover some of the subcomponents which are smaller subcomponents, but they are very important in the overall performance of a PLL. Now, first thing we are going to look at is a phase frequency detector, right? And then it is somehow related to your charge pump and to loop filter. Now I'm going to devote a separate section for loop filter design later on. I'm just going to show you the nature of a loop filter. So ultimately what happens is, now let's say this is a VCO and this is controlled by a control voltage. So this VCO basically is fed with a voltage which comes from a loop filter, and this is a third order loop filter which I'm going to design. So its basic design looks like this, right? Right. So its basic design looks like this. Okay. And here you have got two resistors. Okay. So let's say this is C1, one capacitor, C2, and then okay, maybe I have done a little bit of, yeah, so that's fine. So C1, C2, and let's say C3, and then you have got R2 and let's say R3, right? So this is the nature of the loop filter. Now if I look at this node, right, is a floating node ideally, right? So this node is a floating node, right? Because you see there is no path to ground. Now what's over here inside a VCO is something of this nature, and then there are two vectors. Okay, so basically this goes to the center of that vector. So there are two vectors, or rather I would draw it opposite, so because these are reverse bias diodes, right? So let's draw them this way. Okay, so this is going to the center tap here, and this is going here, and these are going to across your tank circuit, right? So this, okay, is let's say bypass, and this is okay, bypass cap. Now if I look at this, so basically this goes in here. So if I see that the entire structure, if I assume these diodes not to be leaking any current, right? So if I look at the diode characteristics, you would know that a diode basically just behaves like this, and then it becomes asymptotic at a place which is your turn on voltage of a diode. Let's say that is phi 0. So somewhere near phi 0 by 2, this diode starts conducting, so this falls off. So now what happens is I am going to tune my VCO in this range, right? This is what we are doing, right? We are tuning this VCO in this range so that I can get a maximum swing of this capacitance, and this capacitance basically varies from here to here. So this is the variation in the capacitance. Okay, so this is how the VCO works. Now what happens is, at low frequencies I have no issue. Over here there is going to be low frequency, sorry, over here there is going to be high frequency because the capacitance is low, and here I don't have a issue. The issue comes at lower frequencies. At lower frequencies, these diodes they start losing charge because they start getting forward biased, and this causes the current to be pulled from here, and this causes these capacitors basically to lose the charge. So there is always a droop at low frequency, and we have to take care of that droop. Okay, one way is I have some form of a buffering mechanism over here, right? So if I have a buffering mechanism over here, okay, I would be able to supply current and still hold the voltage to be constant here, right? So that VCO basically doesn't change the frequency, right? So this we have to be careful of. Now this basically uh, dictates what the charge pump is going to be, right? And the nature of the loop filter, okay, also dictates that. Now charge pump itself has its own leakages, right? So now you know what is a loop filter and what is the source of leakage in a VCO when I directly, you know, control the VCO by this loop filter voltage, output voltage. Now let's look at what a charge pump is going to be. So I am assuming that a charge pump has got a high impedance source, okay, high impedance because there is a reason for having a high impedance. Again, I want to minimize the leakages. Okay, so I have a high impedance source, which is current source, right? Current source, which is going to source the current into the output. So one of the paths is going to be, let's say these are your transmission gates, right? So one of the paths here is going to the loop filter, right? Loop filter, right? And similarly, there is another path which is going to the ground, right? So these are nothing but your transmission cells, and this path is going to the ground, right? So here I am going to have some form of a high impedance sink, right? So here I am going to sink the current if I want to pull the voltage, the output node voltage down, right? Now besides this, I would need some kind of a tandem arrangement here, okay? And this tandem arrangement, okay, so basically this is your tandem arrangement, and similarly here I'm going to have a tandem arrangement here. And what this tandem arrangement is going to do is either this path or that path kind of thing, right? So either the current is basically pulling this node up, or this current has to be, you know, sunk somewhere, and this basically is done by a you can say by a MOSFET here. Okay, so I am going to connect this MOSFET. Okay, so basically I'm going to connect this MOSFET as a diode, right? So this is how the pull up is going to take place. Either the current is going to the load, so basically the current is going to the load, or the current is steered this way to ground, right? And similarly I have this tandem arrangement here, okay, this tandem arrangement is over here. This is controlling whether the current is being sunk here, or basically the current has an alternate path to be sunk here, right? So and this would be another diode, okay, which would be connected somewhere, something like this. So this I am going to sink here, right? And when I show you the diagram, you will clearly know what's happening. So now the either the output capacitance of the loop filter is going to be discharged this path, or it is going to steer a current here this way, right? And these two, so these two are controlled by, so this is controlled by a up pulse, and this is controlled by a down pulse, okay? And here I'm going to reverse the role, because if you remember here, a lower voltage results in a higher frequency and a higher voltage results in a lower frequency. So I'm going to reverse this role here, right? So the pulses here are going to be down, and the pulses here are going to be up, because KVCO is negative in my case, okay? Okay, so this is my charge pump, okay? So I have looked at loop filter and I have looked at charge pump. Now there is an issue here again. The issue is what happens during this current steering transition. In this transition, okay, I don't want the output capacitance of a loop filter to lose its charge back into here. So what do I do at the output? At the output, I am going to have another combination, okay, which is going to give you a what you call uh, a trickle charging. Okay, so basically I am going to draw dotted here. So this is going to give you a trickle charging, and then this is connected in tandem. Okay, so this is connected again in tandem like this, right? So what it's going to do, it's going to provide a high impedance. Okay, so that's your high impedance when basically there is a transition going on, because the transients are going to discharge the output capacitances. Okay, so I don't want those transients to be discharging the output capacitance. So what I'll be doing is I'll be having one transmission gate which will be basically providing a high impedance when this transition is taking place. Okay, other is going to do something called trickle charging, right? So it is going to trickle charge the output capacitance. So these are the parts of the charge pump. Now this basically dictates how the PFD is going to operate. So the whole goal here is a PFD design. Okay, and the PFD design works as per this table. Okay, so this is a high impedance state. So this is basically the high impedance state when um, the the PL is locked to the desired frequency, right? And let's say that I have FREF come first, okay, and FDIV. So let's say there are two inputs to a PFD. Okay, PFD has got two inputs. One is your FREF, which is coming from the crystal. Other is coming from the multimodulus divider, that is called FDIV, right? So if FREF comes in first, right, that means that the PLL is operating at a higher frequency. It has to be lowered in frequency. So lowering in frequency is basically I have to pull this node up. This node I have to pull up, right? So I have to issue a state. So there is going to be a state here which is going to be a up state. Okay, so if FREF comes first, right, and then FDIV comes, right, so it is going to be in this state. So let's undo that. Okay, so this is going to be the state. Okay, so this is going to be a state where the node voltage, the output node voltage of a loop filter is going to be pulled up, right? So this is the up state. Now if FRF continues to come higher, then it is going to remain in this state. Okay, now if FDIV comes first, then I will go out of this up phase. So if this FDIV comes in, I'll go out of this state into a high impedance state, right? So this is how one of the states is working. Now if FDIV comes first, so if FDIV comes first, okay, then I am going to be in a state which is going to be a down state. And why it is a down state? Because my KVCO is negative, right? So it is going to pull the voltage down to advance the frequency, because FDIV is coming before F. Have I messed this up? I think I have reversed the role. Let's start over again. Okay, I want you to have this clear. Okay, so what's happening is, let's say FDIV comes first, which means that so this is FDIV. So FDIV comes first means that the VCO is running faster. So basically if VCO is running faster, then FDIV is coming before FREF, right? So this would require me to up the voltage so that VCO basically slows down, right? So up the voltage here so that the VCO slows down. So this will be in the up state. And then when I keep doing this, so at one point this FREF will come first, right? When FREF will come first, then it is going to go out from the up state to the high impedance state. On the other side, if FREF comes first, so this is FREF. So if f ref comes first, that means that the VCO is running slower. So if VCO is running slower, I have to up the frequency, which means I have to down the voltage. So it will go to the down state because my KVCO is negative, right? In a positive KVCO, the roles would be reversed. Now I keep doing this, right? If FREF keep coming first, I keep issuing the down pulses, and a point comes that I am going to have FDIV come first, and I'm going to go out of this down state back to a high impedance state. So in the high impedance state, okay, PLL is locked. So PLL is locked here. Okay, so this is how my PFD works. Now there is something funny about this PFD which I'll try to explain is the following. I can use, so for example, let's draw the waveform. Okay, so let's say that this is your FREF. Hang on. So let's say this is your FREF, and what kind of circuit you have to design. Okay, so what's happening is, let's draw now FDIV, which is coming at a later stage because it is running slower. Of course, this is going to slide. So if it is the frequency, if it is the phase, then it's just differing in phase. So this is basically running slower. Okay, so now what is going to happen is this point and this point, right? So of course, you know, I should be doing at the rising pulses or at the falling edges or rising edges, right? So it is not a dual clock edged. You can design a dual clock edged, which I may cover later on, right? So let's say not over here. So this is basically a wrong description. Let's compare on the falling edges only. Okay, so now I have this falling edge, this falling edge. Let's draw one more. Okay, and I have this falling edge, and compared to this, okay, compared to this, my FDIV falling edge comes later on, right? And then what's going to happen is, for this region, okay, I have to have a, so in this case FREF is coming first, right? Right, so I have to put a down pulse, right? So in this case, for this region, I have a down pulse, right? And similarly over here, okay, so I have a down pulse like this, and again over here I have a down pulse here, right? So this is your down pulse because your diff is coming later on, means that it is running slower. That means that the down pulse is going to lower the voltage so that it runs faster. So if you want to remember this chart. Okay, so KVCO is negative, so I have to down the frequency. So this is your down pulse. Now what's happening in this case is, I can design this using a simple XOR gate. Okay, whenever they are not equal, I am going to have a pulse, right? So this is when they are not equal, that's a XOR state, right? But then XOR is also going to come over here, which I don't want, right? I want to take decision only on the falling edges. Okay, so XOR, you know, I'm not going to use XOR. Okay, so I'm going to design a circuit such that the output of the PFD goes up, okay, when whichever is the first edge. On the second edge, I have to look it on a different waveform. So let's say I'm looking on this waveform, so this down will go up, right? Down pulse will go up, and when I am looking at the falling edge of the FDIV, then it is going to go down. So basically decision is taken on two falling edges. One is of the FREF, other is on the FDIV. So whichever comes first causes a pulse to rise, and whichever comes later causes the pulse to drop. So you understand what is the the operation of a PFD. The operation of a PFD is controlled not by one clock. It is controlled by two clocks. In one case, it is going to be the first one is going to cause it to go up in state, and the second one is going to cause it to go down in state, right? Okay, so the clocking is taking place on the falling edges. Whichever falling edge comes first, okay, that is going to do the set function, and whichever comes later is going to do the reset function. Now let's reverse the roles. Okay, so let's basically say that fref is faster, uh, fref is slower, sorry, ff is slower than fdiv. So VCO is running at a higher frequency, and then what is going to happen? Okay, so this is your edges for decision, and then I'm going to say that uh, this is coming faster, right? So how would I do that? Okay, so this is running faster, so this is coming faster, this is coming faster, this is coming faster, like this. Okay, so these are the edges for decision. So in this case, what I'm going to generate is a up pulse. Now how do I generate the up pulse? So whichever edge comes first, right? So whichever edge is going to come first, okay, this is going to cause the set to take place, right? And then the edge coming later is going to reset it, right? So this is going to reset this. Again, on the falling edge, the decision takes place over here, and then the clear decision, rather I would say not reset, I would say clear. Okay, clear. Okay, so the clear decision comes on the second edge. So the first edge is going to set it, second edge is going to clear it, whichever comes later is going to reset it. So this is what happens when the V this is what happens when the VCO is running at a higher frequency. Okay, so I'm issuing up pulses here, right? So what it's going to do is it is going to take this node voltage, control voltage of VCO up, so then the VCO starts running slower, right? So that's the basic principle, right? So in this case, hang on. Okay, so what's happening is you are issuing up pulses when the VCO is running faster, is it? VCO is running slower, sorry. So when VCO is running slower, you issue the down pulses, and when VCO is running faster, you issue the up pulses, and KVCO is negative, right? So the two cases we have seen here. So whichever edge comes first, okay, whether it's fref or fdiv, is going to set the output, and whichever edge comes later is going to clear the output, right? So this part we have to understand clearly, that the first edge is going to set it, and the second edge is going to clear it. Now what is going to happen is the clearing function is like a feedback, right? In this PFD, the clearing function is like a feedback. So what happens is, if the feedback takes a delay, okay, so let's say the feedback takes a delay, then this edge which you are seeing over here, okay, would get delayed, and these edges will become bigger because there is a delay in the clear function. Similarly, that same delay in the clear function is going to do this, that this edge would clear later on. Okay, and this is because of the delay of the clear, right? And this results in what is known as the dead zone. So in dead zone, the PFD fails to respond, okay, in time. So you are delaying the down clear or the up clear pulses, right? So that is basically the dead zone of the PFD. And what this dead zone does is that the voltage which is supposed to stabilize, right, is going to oscillate, like, you know, the voltage is going to oscillate. So instead of this voltage being a pure DC, okay, it is going to do this. Okay, so when this does that, what's going to happen is that you are going to have the PLL locking, unlocking, locking, unlocking, right? So this would result in a noise, okay, a phase noise, which is not desirable, right? So the dead zone has to be avoided. Okay, so I hope you understand what is the role of dead zone. The dead zone is when the PFD fails to respond to a clear action because of the delay in clearing it. Okay, so this can be overcome by the following mechanism. Let's say I draw the up pulses here like this. So let's say these are my up pulses. Okay, and the down should be silent, right? The down should be silent at this point. Now if I want to remove the dead zone, I might give some bias to the down. Okay, so it kind of approaches first. Okay, so there is an overlap region here. Okay, this is perfectly fine. Why this is fine? This is fine because if the up and the down currents are the same, so source and sink currents are same, I source is equal to I sink, then if these two pulses are balanced, right? So in this region, okay, the output node will neither uh, charge nor discharge because the source current is same as the sink current. So the the output of the charge pump is going to be constant. It's neither going to be charge discharge. And what it does is it gets rid of the dead zone. Okay, so it is getting rid of these dead zones, right? Similarly, if I was issuing down pulses, right? So let's say that these are down pulses, let's say. Okay, so if these are down pulses, then the up should be silent, right? But what will happen is if I was to remove that dead zone, I would be introducing a very thin. So this is a case of up, so this is a case of down, but then at the same time I'm issuing some up also. So I hope you understand how I can get rid of down. So the clear is basically advanced, or rather, you know, the clear is basically balancing it out. Okay, so I will get rid of dead zone as long as I source is equal to I sink, these two currents are matched, then the output node of the loop filter is going to have a constant voltage, right? So this is what happens if I remove the dead zone. Now let's say, what about the steady state? Okay, in steady state, okay, what is going to happen is I am going to have these pulses which are going to be like kind of a beat frequency kind of thing. These pulses are continuously coming, and similarly these pulses are overlapped by the other pulses. So you understand what's going to happen. So in this case, this is a up case, this is a down case, and this is when the PLL is locked. So when the PLL is locked, I am still getting up and down pulses, but they are equal in width. And that means that if I source is same as I sink during the duration, then the output node of this loop filter, right, or the charge pump output node is going to hold at a constant voltage. Okay, so this would be called a zero dead zone PFD. Okay, now let's look at some of the figures. Okay, so this basically circuit looks like this one. Okay, and this is the state diagram for the PFD, which I have just explained you, right? So here is the reset part, and when reset have a delay, then you have a issue, but this one is not going to have that issue. So I'm going to design this circuit with fully differential circuits, or PPCL gates, right? And the purpose of these gates would be, now if the VCO is operating at 5 gigahertz or more, or even 2 gigahertz, that's a high frequency. But here all these circuits are going to operate at FREF, nearly FREF. So that would be 40 megahertz or 80 megahertz or something like 100 megahertz, right? So these are slower circuits. So when these circuits are slower, you can make the transistors to be smaller. And the advantages of making smaller transistor, okay, because they don't have to function fast, right? So the advantage of using smaller transistors is you are going to minimize the leakage, right? So leakage is everywhere. So I am going to use, so if you see this, everything is made up of NAND gates, right? So I am going to use NAND gates to design this, right? So this is our exercise for today. And if I show you the response, okay, so you can see if div leads the ref, fdiv leads the ref, then what's going to happen, right, in terms of uh, div and ref. So that's basically your div and ref frequencies, right? And then the corresponding up and down pulses are over here, right? So in this case, up pulses are coming with a slight overlap of down pulses. Now in the other case, if ref leads the fdiv, then the down pulses are coming, and then you have a slight overlap with the up pulses. This is what I explained you here in zero dead zone here, right? This is what I have explained you. Okay, so this is what's happening in the response. And if you look at what happens when they are really close, like let's say the PLL is locked, okay, so I'm simulating that as, let's say, 10 picosecond of delay. That 10 picosecond is also showing up as a delay here. You can see that when the delay is going to be 0 picosecond, then the two pulses up and down are going to completely overlap. Okay, so that's what I was trying to show you. So there are three states. One is div leads ref, ref leads div, and when ref and div come together, what's going to happen, right? So this is a zero dead zone PFD. Okay, another thing I want to show you is this charge pump, which we have already looked at, right? So this clear bar, which are controlling the trickle circuit and the high impedance circuit, is also coming from the PFD, right? And then there is a up bar and down bar, right? So these are also coming from PFD, and the basic structure I have discussed, right? So this is there. And then these current mirrors are going to be cascade current mirrors, right? So here they are going to have high impedance. So here I'm just showing you source and sink impedances, and here I'm showing up the buildup of charge pump voltage, right? So if I look at the two conditions, up and down, okay, then you have the red one which is pulling this up, and the green one, basically the down pulses, are pulling it down, right? So these are the two cases here. And then when the both are matched, then up and down come for a very short duration, they come together, right? So that represents this flat voltage, or the final voltage, or the steady state voltage. And then I'm going to discuss this loop filter later on. So let's go ahead and design a PFD. So for this PFD, it's a fully differential. That means I have to design a PPCL NAND gate, right? So I'm going to design a PPCL NAND gate. Now, I'm calling it a NAND gate, but you know, this is a universal gate, because you know it's a differential that allows me to use this as a NAND gate or a NOR gate. It really doesn't matter, right? So that's what I'm going to design right now. Okay, so now we are going to construct this PFD using transistors. So I am going to first make a PPCL NAND gate. So I'm going to just say file, new, and cell view, and I will call this as NAND, and I will put a subscript slow, because what I'm going to do is I'm going to make long length devices which are going to be lower leakage, right? So that's what I'm going to do here. Okay, so the design is going to be something similar to a NOT gate. So let's copy that NOT gate. Okay, so that's your NOT gate. So I'm just going to copy this portion of that NOT gate. C, and that's going to be over here. Okay, so what I need to do here is the following. So I want a NAND function, right? Okay, so I will repeat this transistor over here. Okay, so let's get rid of these connections. Delete, 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 delete. So let's get rid of these connections. Okay, so this is our negative resistance circuit. This is for your, you know, transition, faster transition, right? So I am going to take this one. So all are NMOSes, right? So I'm just going to repeat this over here. Okay, now before even I do that, what I want to do is I want to go here Q, and this one I want to make 260. So basically this is a longer channel length, right? So this is going to be 260, right? And similarly I would do for every transistor, 260 nano. I can do this with a negative resistance also, 260 nano. Okay, so all the devices are 260 nano, right? So basically I am using a longer channel device for a better leakage performance. So I am going to do something like this, right? And this contact is basically your P sub, right? Similarly, this contact is P sub, and this is your ground. This is the output node. Correct? And then I have to repeat this one over here, and I have to repeat one over here. So the design is very simple. Right? Okay, so all the bodies are tied to P sub, right? So you just can verify all the bodies are tied to P sub. Okay, and this is in its val, so it's tied to the source. Now I'm just going to do the connections, right? So okay, so I'll do A and A bar. Okay, so I need to do, so first of all, let me put the VDDs and other pins, right? So I have got VDD. So let me just minimize this. And this is your VDD. And then I have got ground. And this is your ground. And then I have got P sub. That's a P sub. So now these power rails are done. Okay. Right. Now the question is A and A bar. Right. So let's do A. So let's say this transistor is A. Correct. And this one basically is also driving this one. And then you have got A bar. Right. I did some mistake, I think. So let's do a undo for that connection. Okay, so this basically is driving that. So this basically is driving that. Right, so this is A, and then you have got A bar. Let's see if I'm recording. Yeah. So now you have got A bar, which is going to be this guy. And this basically is driving that. So that is your A bar. Then you have got B and B bar, right? So let's put here B, which is going to be this transistor, and this is driving this one, right? So this is your B, and then you have got B bar, right? So where would I put B bar? B bar, and this transistor is your B bar, right? So this transistor is your B bar, and this basically is driving this guy. Okay, so these are fine. And then you have got Q and Q bar, right? So this is a Q bar and the other side is a Q, right? So let's put here Q. So Q is this, and then you have got a Q bar. Okay, so Q bar I'll paste somewhere. Over here. Okay, so this branch is a Q bar, and the other branch is a Q. Okay. So that's your NAND gate, PPCL NAND gate, right? So I'm going to very quickly create a symbol for this PPCL NAND gate, right? Okay, so check and save, then create cell view from cell view, and here I have got A and AB as a left pin, then B and BB are left pin, right pin are Q and QB, right, and bottom pin are ground and P sub. So we have consumed A, B, 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 ground, Q we have consumed Q bar, and then P sub. Okay. So I'm just going to change the symbol slightly, right? So let's say this one, and this one. Okay, and this guy I can get rid of, right? So I don't do a mistake. So I just, okay, fine. So just to remind myself that this is a bar, I'm going to put bubbles, right? Part name here and ground here, P sub here, and this thing goes here. Similarly, VDD over here, and this goes here, and then Q goes here, and Q bar goes here, and this is your path, and this is your instance. Okay, so I'm going to introduce here a bubble. So let's just do that bubble. Okay. Okay, so this is that. This is that. This is that. So that's my PPCL NAND gate. So I'll just do a check and save here. Done. And check and save here. And done. Okay, so now that we have PPCL NAND gate, let's go ahead and construct the where is it? Did I close it? Okay, so I'm going to construct this circuit, right? So this circuit, you can see, has got two paths which are symmetric. Okay, one part is over here, other part is over here down. So I'm going to make a symmetric part, right? And I will call this one as PFD half, right? PFD half. That's what I'm going to do. So here there are two in this half. In this half, there are two symmetric cross coupled pairs here, right? And then there are two NANDs which are sitting here, right? So that's what I'm going to create. And then I have to generate an additional what you called uh, besides up and down, right? So basically one goes here, down and up, and these are inverted because of KVCO being negative. Okay. Okay, so let's go ahead and construct this. Okay, so I am going to uh, create a new category and call this as PFD circuits. Okay, and I'm going to modify this one to include the PPCL NAND gate, right? Okay, uncategorized OP mixer and mixer. Okay, output mixer. This part I'll cover later on. Okay, so don't worry about that. Okay, so now let's go to where did I place this? PFD circuits. Fine. So I'm going to create a new cell view and call this as PFD up or PFD half rather. So I'm going to do half functionality, right? So in this case, all I need is a NAND gate, right? So I will say insert PPCL NAND, which is going to be here, PPCL NAND gate, right? And I need two cross couple gates, so I'm going to just copy these. Okay, so these are two cross couple gates, right? I want to repeat this structure also, right? So let me do this. So this is your VDD, and this is your ground, and this is your P sub, right? So these are connected now. Then I have to cross couple it out, right? So Q goes to A and Q bar goes to A bar. So I'm just cross coupling them. So this guy will go to here, and then this guy will go to here. So this is cross coupled here. And similarly, I would have Q go to B, this Q go to B like this, and this Q bar go to, sorry, I did a mistake here. Q goes to B and Q bar goes to here, so I want some space over here. Okay, so if I move it doesn't matter. Okay, Q bar goes to here. These are cross coupled, right? So this leaves behind two inputs, right? Okay, now one of the inputs will come from here. Okay, but I have to just repeat this structure again, right? So I am going to take this structure, copy this. This is just a cross coupled structure. I am going to copy it over here, right? Okay, so next is I'm just going to connect all the VDDs together. So this is VDDs tied together, and then I'm going to tie the grounds together. So that's a ground tied here, and this one has a ground over here, right? So I have to tie it to the ground, and then I have to tie the V sub together. P sub, sorry. So that's a P sub. How do I reach there? Okay, I have reached the P sub here, and this one also has a P sub which I have to reach over here. Okay, so ground, VDD and P subs are tied together for all of them, and then its output goes in here, and its output goes in there. Its output goes in here. Correct? And then you are going to have, right, so then you are going to have certain pins which I'm going to place, and then the output, right, I have flipped. Okay, so I'm using certain buffers in here, so I'm going to use some buffers in here, right? So I'm going to insert PPCL NOT gate here. Browse PPCL NOT. Right, so I am going to have 4-stage buffering here. Make sense? 1, 2, 3, 4. Okay, so that 4-stage buffering over here, so that's not going to change the logic function. And then the supplies are connected together, and then the grounds are connected together, and then the P subs are connected together, right? And then they are combined to the overall circuit. So basically this node is a VDD node, this node is a ground node, and this node is a P sub node. Correct? So these are connected, and here I am, because those are your there is a NOT gate for the output, so I'm going to flip this out, right? So Q will go to A bar and Q bar will go to A. So this is done. Now I have to just put the pins in here, right? So I am going to put here VDD. Just 1 second. Okay, so let's just add the pins, right? So first of all, I'm going to add VDD. that I'm going to put here, and then I'm going to put ground, and I'm going to put that ground over here, and then I'm going to put P sub, right? So just making sure if P sub is connected properly, right? So here I'm going to put P sub, and P sub I'm going to keep over here, and I'm just going to connect them, my supply rails first. Okay, then I have got ref bar and error, right? So error is basically your nothing but your reset, right? So I call it EE bar, but it's okay, you can call it anything you like. Okay, so I have got a ref over here, and then I have got ref B over here, and then I have got E over here, and then have got E bar, EB over here. So that's all covered. So I have ref bar, E, and E bar. Great. So these inputs are done. Ref bar, E bar. Right. And then there are two more inputs, which is B bar, which is over here. So I'm going to put a pin here. So B, and then I have got B bar, it's over here. Okay, and then I'm just going to connect them, B and B bar. Correct. And then the outputs, right? So this one I'm calling down and down bar. Down and down B, kind of reverse. So let me just rotate this out. Okay. So I have got down, and then I'll insert one more pin, sorry, and that is called down bar. So that's over here. Then I am going to do two more output pins. One is going to be O bar, and so I'm going to do O. So O people confuse with 0, but it's a capital O. And then I have got O bar, OB. Right, so I'm going to take this output from here. That's O. That's O bar. And then I'm going to get the same output on this side. Okay, that I'll call FF bar. So both are same actually. Right, O bar, and then you have got F in F bar. Right, so let me get that. So F, which I'm going to get from here, and F bar. Correct. So I'm getting F from here and F bar from here. Okay, so I have done the 1/2 of the PFD. Correct. So I think I have covered all the pins. Okay, so I'm going to create a symbol for this. So I'm going to say check and save. Two warnings, let's check them. Okay, what's the warning? Floating A bar on instance I4. Instance I4. Is this instance I4? This is I8. Where is it floating? I5. It's hinting here. So I don't understand that. On I4. I4 it is floating. I2, I1, I0, I4. Oh, these two. Okay. So I forgot to connect where they go. Okay. Okay. So basically they are driven that way. So they are floating. So they are driven by this A and A bar. Right. Okay. Okay, now everything is okay. Check and save. Right. And here. Okay, so now we have this in place, and if I do check and save, everything looks okay, no errors, right? I'm going to make a symbol for this one. So I'll go to create cell view from cell view, say okay, and let's say how I want to keep the pins. Okay, so I'm going to put ref bar on the left. So I have got ref and ref B. Okay, and then on the right I'm going to put down bar, F bar, and O bar. So I'm going to put down bar, F bar, and O bar, right? And the bottom I'm going to put uh, B bar, E bar, B bar, right? E bar. E bar is basically the feed point for the feedback, right? E bar, ground and P sub, ground and P sub. Okay, let's see which I have consumed. I have consumed B bar, down bar I have consumed, E bar, F bar, ground, O bar, ref bar, VDD remains in P sub. Correct. So this is there, and here I'm not going to edit any of the stuff here. So this is one half of the PFD. I'm going to do check and save. Done. Close that. Close that. Now I am going to construct the PPCL PFD. So I'm going to construct the PFD now. Correct? So I am going to make a new design, and I will call this as PFD. Okay, just 1 second. Okay, so let's make a PFD now. Sorry about this. Let's make a PFD. Okay, say okay. And here I am going to have PFD half, right? So I'll say insert, browse, everything PFD half, right? So I have got two halves of the PFD, right? And I am going to need two NAND gates. So these will be your PPCL NAND gates, two NAND gates which are under here. So I'm using two NAND gates, right? So let's put in two NAND gates. So this is the one which is feeding back, right? So one of them is feeding back, and then I'm going to put two NOT gates, insert to buffer the output. So browse PPCL NOT. So I'm going to put in two NOT gates. Okay, and so this is all I need. So first what I'm going to do is connect all VDDs. So that's a VDD. So all the VDDs are connected. Then I'm going to connect all the grounds. Sorry about this. Okay, so grounds are connected. And then I'm going to connect all the P subs. Correct? So these three lines are done. Then I am going to connect these, right? So the output goes to buffering. And this function is nothing but CC bar, which is going to control the trickle circuit and the trickle recharge and basically the output high impedance. So that's what it's going to do. And its output is going to drive that. And then we have got a down in down bar, right? Okay, so you have down and down bar, so that will be down and down bar. So let's start putting the pins, right? So we have a VDD. Sorry about this. We have the VDD pin, then we have the ground pin, and then you have got the P sub. So this is your P sub, this is the ground pin, and that's the VDD pin. So all are connected, and then these are your down bar, up bar. So you have got down. So these pins are your down bar. So I can put them here if I want down bar. Correct? These are your down bar. Then you have got up bar, right? I need to rotate it out. Okay. Then you have got up bar. So that's your up and up bar pins, correct? And then you have got the two outputs, okay? The two outputs of the, so that's the feedback point, right? So you have got two feedback points which will go into the error, right? Or BB bar, feedback points, right? Okay, so I'm going to use this NAND gate for that purpose, right? So I'm going to take FF bar and NAND them out. So that's a feedback point, F and F bar. Similarly over here, F and F bar. Okay, and this is going to your feedback point, right? So 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 Q goes to, okay, correct. So this is going to go to the feedback point B, and of course this will also go to B. How can I straighten this out? So this is going to go to B, and this one will go to B bar, correct? Which has to go to B bar, correct? So Q is feeding back to B, Q is feeding back to B, and Q bar is feeding back to B bar, right? Okay, so that's done. So that's your feedback, and then the outputs, right? So basically, hmm, okay, so O and O bar, they are flipped out. Similarly, O and O bar, they are flipped out. Okay, let's make sure of this connection. Okay, so E is basically enable, right? So if I want to permanently enable it, okay, so if I want to permanently enable this one, so E will go to VDD, correct? And E bar should go to ground. So this is enable for these half cells, right? So let's do that. E bar will go to ground. So E is going to the supply and E bar is going to the ground, right? So E is going to the supply and E bar is going to the ground, correct? So this part is covered. Now the two inputs are ref and div, right? Two inputs are ref and div. So let me see if I'm recording. Yeah. Okay, so I have got ref. So I need the ref which will come from the crystal oscillator. Ref which will be here, and then I have ref B which will be again from the crystal oscillator, and then you are going to have div. That div will come from the multimodulus divider, and then you have got div bar. Uh, sorry, div bar. Okay, so ref bar from the top one and div bar on the bottom one. So this is the two halves of the PFD which are symmetric, right? So that's why I created one circuit and repeated it. Okay, so this is done. And then this one is going to be C bar for the output stage of the charge pump, right? So I am going to call this as C. So C would be on this side, and then I am going to have CB, C bar, which is going to be here, and I'll just connect them. So this is C bar and this is C. So in essence, I have generated this stuff, right? This stuff I have generated, and this enable basically is E bar, and that enable is permanently connected to, you can have a logic function for enable also, but for now I am connecting enable to the VDD. Am I right? Yeah, enable to the VDD and enable bar to ground. So these are permanently enabled, right? So I guess I am done with this, right? Now the idea is to check this. So I am going to first make a symbol for this, right? So bear with me a second. Okay, so let's make a symbol for this one. So I am going to say create cell view from cell view. Say okay, and here the left pins are going to be ref and ref B, and then I am going to have div and div B. Div and div B are the left pins, right? And the right pins I'm going to keep here as up, and up bar, and then I'm going to have down and down bar, right? So these are going to be right pins. Then the bottom pins are going to be ground and P sub, right? Ground and P sub, and the pins which are left are going to be CC bar. So basically CC bar. So let me create CC bar. Okay, so CC bar I'm going to leave at the top. Div and div bar are consumed. Down and down bar are consumed. Ground is consumed. Ref bar is consumed. Up and up bar is consumed. VDD is at the top and P sub is at the bottom. So we have consumed all the pins here. Say OK. So this is my PFD, which I'm just going to save as is, and I am going to just close this one. Okay, so now I am going to make a test bench, right? So I'm going to say new cell, and I will call this one as test PFD, right? And say OK. Make sure I'm recording. Yes. So here I want to insert the PFD. So insert everything. I have a PFD which I insert here, and then I am going to just to drive them, right? So to drive them, okay, so to drive them I'm going to use, okay, I'm going to use V pulse, right? And this output I'm going to terminate in 10 femtofarads, right? And CC bar also into 10 femtofarads. So I am going to say insert an analog lip. I'm going to take a cap. Okay, so I'm going to take a cap. Out. Analog lip cap. And this is going to be 10 femto. 1, 2, 3, 4, 5, and 6. So you have got up bar, down bar, C and CB, and these are all connected to ground, and B sub is also connected to ground. Okay, so I'll insert a ground here. I say G and D, ground, that's a ground. And then I need a VDC. Well, okay, V is small maybe. Okay, so we have a VDC, and its voltage I'm going to operate from 2 volts. So that's your 2 volts of VDD. Correct. Now the question is, I want to generate the ref bar and down bar, right? Okay, so I'm going to use V pulse. Let's see if V pulse works. Okay, so for V pulse, okay, so I am going to have the second voltage as 2 volts. and I need to put period and delay. Okay, width, period, delay. Okay, pulse width, period. So period, let's say put is 20 nanoseconds. Width is going to be 10 nanoseconds. Correct? And then rise time, fall time, okay, I can put as, you know, uh, 1 nanosecond. So I'm operating way faster than uh, what the, because 20, so basically 1 nanosecond is 1 gigahertz, so 10 nanosecond is going to be 100 megahertz, right? So this is going to be 50 megahertz, isn't it? Yeah. So uh, let's put 10 pico as a rise time and 10 pico as the fall time. And delay, I am going to put here. Do I need a delay? Okay, here I don't need a delay, right? So here I don't need a delay, so that's fine. So this is going to be ref, and then ref bar is going to be swapping this. So first I'm going to check these only. Okay, and the other ones are going to be the same, but then I'll introduce a delay, right? So in this case there is no delay here. So this is your ref, this is your ref bar, and then I am going to put in a delay. So let's look at the figure which we are trying to do. Okay, we are trying to do this. So I'm going to give a delay of 3 nanoseconds, right? 3 nanoseconds, and 3 nanoseconds lead and lag, and try to generate the output. Okay, so I am going to copy this entire thing over here. Okay, and that's fine. Only thing I'm going to do is I'm going to put a delay of 3 nanoseconds. So in both I have to put a delay of 3 nanoseconds. Okay, so I have put delay of 3 nanoseconds on both of them, right? Okay, so the remaining thing is the same. Supply is fine, ground is fine, outputs are fine. Okay, so let's just go ahead and simulate this. So just say check and save, and if it works fine, if it doesn't, I'll debug it. So launch ADL, and here I'm going to do a simulation. Okay, so let's say for how long I'd want to simulate this. 120 nanoseconds, right? So I'll go to analysis, choose transient, 120 nanoseconds, conservative, so okay, and then to be saved. So I'll say output to be saved, select on design. I want to look at ref and ref bar and diff bar, and then I want to look at up bar, down and down bar, right? So this is what I want to look at. So let's go ahead and run this simulation. So fingers crossed, if everything is fine, I'll get the waveform. If not, I'll have to debug it. Okay, so what do I need to plot? I want to look at div and ref. So I want to look at results to be plotted. First of all, I want to see div and ref. So I'll go to main from. Okay, I want to look at ref and I want to look at div. Right, so basically they are delayed, and if you want you can look at ref bar. Of course it will be the inverse of that, and div bar, that's going to be inverse of that. So let's just separate them out. So I have got ref and ref bar, div and div bar. So I'm going to just get rid of these. Okay, so I have this delay, and then I want to see up and down, right? So up and down. Okay, so now you can see this, that there is a down pulse here and then there is an overlapping pulse here, which is same as over here, right? So you have got down, up pulse and then down as that. So you have the darker one is the up, right? So let's see over here. The darker one is the up. Okay, it's kind of reversed. Let's see, what did we do? We said that div div is lagging, isn't it? Div is lagging. So is basically this figure rather. So you have got this up and down like that. Okay, right figure. Okay, so this div is lagging. Now I want to see the other side, which is when div is leading, right? So for div to lead, so right now the PFD is working fine. Okay, so let's see what happens if the div leads. So I'm going to go here and I'm going to insert delays here, Q, put here 3 nanoseconds, okay, and Q 3 nanoseconds. Right, so now I'll remove 3 nanoseconds from here. Okay, so now the div is going to lead by 3 nanoseconds. Q, delete, apply. Let me just check. So delay is removed from here, delay is removed from here, delay is introduced in the ref. Okay, so the div is leading now, delay is introduced in the ref by 3 nanoseconds, right? So now the roles, the darker one and the lighter yellow, the roles are going to reverse now. So I am going to go here and check and save this one, and here I am going to say simulate. So what happened? Yeah, it's simulating. So the PFD is functioning for one case. Let's see for the other case if PFD is working. Okay, it's done, and I'm going to go ahead and refresh this. So the roles of light yellow and dark yellow are going to reverse. Okay, so the roles are reversed, you can see here. Now the down pulse is coming as the bigger one and the up pulse is the narrow one. Now let's say if they were together, so there was no delay, right? So that's a locked case, right? So this was okay. Q, there was no delay here. Okay, so basically I have removed the delay from everywhere, so neither leading nor lagging, they are together. So the pulses are coming together, and I am going to simulate now. go ahead and simulate this. Unless some blunder I have done, it should be a very thin pulse for both up and down. Okay, so I'm gonna go ahead and see both the dark yellow and the light yellow should become thin pulses. So I'm just gonna refresh this, and voila. So they are just overlapping thin pulses, right? So that's what we expect. Okay, now I want to see that if I generate 3 picosecond or 2 picosecond or 1 picosecond kind of a delay, then what happens? So I'll go here Q, and let's say the delay is of 3 picosecond. How's that? It's a very minute delay. Apply, and very minute delay, 3 picosecond. Delay 3 pico. Sorry. Okay, so now the delay is 3 picosecond in both cases, right? 3 picosecond and 3 picosecond. So what I'm trying to see is whether it's a zero dead zone, right? So say okay. Okay, now I have a 3 picosecond delay here. I'm going to see if I can capture that. And the idea is, we have seen the overlapping case. Now the idea is to capture this. Okay, now this one is 10 picosecond. I'm trying to do this 3 picosecond. Let's see if it captures that. Well, the rise time is 1 picosecond, right? So let's see if it captures that. Check and save. And I am going to just simulate this one. Simulate. Okay, so I'm going to see whether it's working for zero dead zone. Upload, and I need to zoom in. So basically I'm going to move it over here. This is kind of strange. Yeah. So okay, so now here the delays have to be adjusted because they are not overlapping, right? Okay, but okay, so this is for the design, right? So when I do the design, I will adjust this. Okay, so basically what's happening is, here I am going to get that 3 picosecond here, right? And here, let's check that. Okay, so they should differ in widths by 3 picosecond, but then they should also overlap. Now for that, if you remember, okay, for that I have been putting these buffers around, okay, here also, and if I go inside here also, these buffers have been introduced to match that delay, right? So I will fine tune it, right, so that I get these two overlapping. So these are just the finer optimizations which you do on a PFD when you do the design. But here what I have tried to show you is, you can implement a zero dead zone PFD, which will be that, and that will be this guy. So this is one of the important components. You have to fine tune its performance, and then you have to drive a charge pump with that, and that's going to be the next session. So I'm going to stop here. Thanks a lot. Thank you very much.